Can we get started? Alright, so what we have here is a Van de Graaf generator. The Van de Graaf generator can build up charge on this dome, a negative charge, and it builds up charge by friction. In one of the previous lectures I showed you a Wimshurst machine that builds up charge by induction, by influence. This machine builds up charge by friction, so it's called a triboelectric machine. So this triboelectric machine, called the Van de Graaf generator, can build up voltages up to hundreds of thousands of volts on this dome. And I have a few nice demonstrations to show you. Let me just turn off the light slightly. I think the class starts at 11:30. क्लास का वक्त कितने बजे शुरू होता है? So if you observe carefully, probably you'll see a spark. Now, charge has been built up on this dome, and I have a conducting ball that is grounded. So that charge will leap off from this ball. It will jump onto this metallic conductor and it will be grounded. So hopefully we'll see some sparking here. So if you look at the gap of the spark, it's about 1.5 or 1 centimeter. So this means that the voltage that has been built up on this dome is about 30,000 volts. So because air is normally an insulator, and if you would like to break down the insulating properties of air, one requires over 1 centimeter a voltage of 30,000 volts. So this is micro lightning that is what you're actually seeing here. So here you can see the sparks, and if I just touch this dome, all of this charge will leak away. The sparks. So what is a spark? While this machine keeps on running, I would like to ask you, what is a spark? Why do you see a color here? By? Electric breakdown. How does electric breakdown give you a color?
Due to the electric field.
Due to the electric field. How?
The electrons in the atom will be knocked off.
Right. Right. So what's happening here is that an intense electric field is being applied through air. That electric field can knock off electrons. This process is called field emission. Now when electrons are knocked off, ions are produced. So ions are positively charged, the electrons of course are negatively charged. So the ions and the electrons will move in opposite directions. And as electrons will move, they can move faster because they're lighter particles. They will collide with air molecules, nitrogen molecules, oxygen molecules, carbon dioxide molecules. They will excite those molecules into excited states. Now once these atoms inside air are excited, they will be demoted to the ground level after a certain lifetime, and this demotion to the ground level will produce photons of a characteristic color. So the blue sparks that you see here, the sparks are getting bigger and bigger. The blue sparks that you see here are basically characteristic of nitrogen molecules or nitrous oxide or nitrogen dioxide molecules. So by looking at the color, you can even tell what molecules are involved in this ionization process. And if you observe, the sparks are getting bigger and bigger. Okay. Now I would like to discharge this, and possibly I'll try to show you a demonstration of the Gauss's law. Okay. So what I'm going to do now, I'm going to try out something. I'm going to fix this object on top of this generator. Alright, so this demonstration probably I like to show with the lights turned on. It's best to see this, not the video, for this particular case. So what we have here is the dome that is building up charge, and the metal piece. This metal piece is connected to the metal dome, and it's all metal. At the top we have a metal sphere, and we have two aluminum balls, right? Two aluminum spheres, light spheres that are able to move, and inside this annular ring we also have two aluminum balls that are placed like this. So the top balls are placed like this, and the balls inside the ring are placed like this. I hope you can see what kind of arrangement this is. So what I would like to do, I discharge this. I like to turn on the generator, and I would like to see what happens. Let the charge build up for a little while. Do you observe the balls at the top? They started vibrating, but not the balls in the middle. And these balls at the top, outside the ring, they are repelling one another and they are deflecting away. So these are actually two electroscopes. This is one electroscope, this is another electroscope. I don't want to point my finger here because it's a pointed object and probably the field will be too high at pointed objects. So what I see here is that the balls at the top, outside the ring, they deflect away. Whereas the balls in the middle, inside the ring, they are not deflected. So just observe this demonstration for half a minute, and then I'll ask you what's actually happening here. नजर आ रहा है? ठीक है आपको? चलिए इसकी क्लोजअप भी खींच लें. All right. So could anyone explain to me what's happening here? Raise your hands. How can you explain the fact that the aluminum balls at the top, they are deflecting one another and flying apart, whereas the aluminum balls that are inside the ring, inside the annular region of the ring, they are not moving. They are not deflecting apart. So can anyone explain this, the reason behind this observation? आप बताएं? कहाँ पे? ठीक है. और बाहर? क्यों रिपेल कर रहे हैं बाहर? Exactly. So what's happening here is that on this metal object, charge is being built up. So outside the metal there's an electric field. We all know this. Now this electric field is bathing the aluminum balls outside the metal. So the aluminum balls that are outside, they are inside an electric field. When you place a metal inside an electric field, you build up charge on it, right? So the proximal parts, those ends of the aluminum ball. So these are the aluminum balls that are outside. A charge is built up in the sense that this region becomes positively charged, this region becomes positively charged, and the negative charge goes here. So the positive charges are closer together and they will repel one another, so the balls are repelled. And these charges are built up because these balls are actually seeing an electric field. The electric field that is produced by the charge on this metal surface. However, inside the ring there is no electric field. Then this is something that we learn from Gauss's law. Since there is no electric field, there is no charge that is building up on the aluminum balls. Hence, they are not repelling one another. So how can I actually make these balls fall back? By discharging this metal enclosure. Let's see if I can actually do that. Remember, this is a glass rod this is a glass wand, and the metal ball is on the glass wand. Okay? I move this away, the balls move apart. I try to discharge, so I rid the metal with the charge. The charge goes away, these metal balls are actually coming down, back again. So whenever there is a discharge, the balls fall back. And there is no charge that is being built up on this metal conductor now, because all of it is going to ground. I move this away, charge starts building up, these balls deflect apart once again. However, nothing is happening to the balls inside the ring, because the electric field inside this metal ring is already zero. So this is a vivid demonstration of Gauss's law, nothing else. I move this back. The dome is discharged.
When you even bring the metal ball near, the ball starts to fall even before you can get the discharge.
The question this gentleman has asked, मोबाइल फोन बंद, सवाल पूछा आपने भी, उसकी वजह ये है कि this is a metal, they form two plates of a capacitor. Even before you hear a discharge, or even before you see the discharge, an electric field is set up between this neutral object and this charged object. So there is something that is called a corona discharge. A corona discharge is the discharge before the onset of visual discharge. So before you can actually see the discharge happening, before you can actually see the lightning, the micro lightning, there is still a stream of ions and electrons that is flowing from this object to the neutral object. So even though you can't see it or you can't hear it, still some discharge is taking place. Alright? So I move this back, charge builds up, these metal balls will flee again. Alright? So now I discharge everything, I turn off the generator. Okay? In fact, you can also do the demonstration of holding this, your hair will actually raise. Okay. So I turn this off. And now there's another demonstration I would like to show you. Now what we have here are basically two metal plates. These are circular plates, circular discs. थोड़ा सा फोकस करें इस पे. ठीक है, let me turn off the lights. Let me turn this on. Okay. Alright, so what we have here are two metal plates They are connected to the positive and negative terminals of a power supply. This power supply we built in the lab, it can create up to 20 to 30,000 volts. With the help of a transformer that is called a flyback transformer that's used inside old style televisions. So one can generate a voltage up to of about 20,000 volts in steady state, RMS voltage 20,000 volts, and peak voltage is perhaps of 40-50,000 volts. So these metal plates are connected to this power supply. So a potential difference will build around these metal plates. And I would also like to show you some spectacular phenomenon that may happen for this particular instrument. Alright, first of all, okay, I turn this on. Now an electric field has been set up between the plates. This is something you can actually see over there. I move the plates close together and one can possibly see some lightning discharge. So this is micro lightning. The gap between these plates is around 2 centimeters. So the peak voltage is almost 60,000 volts. I'll move these away. So now I'm below the threshold of the electric breakdown of air because the gap is too large. Even though the potential difference across these plates is still very high, but the electric field is smaller. Electric field we learned today is the gradient of the potential. So the potential difference is still the same. I haven't changed the power supply, but the electric field is not strong enough to break down the insulating properties of air. But if I make this gap smaller, the potential difference remains the same, but the electric field jumps up. And now I have touched the threshold of breakdown. Okay. Alright, now I would like to do something quite interesting. I just touched these plates briefly together. I've turned off the power supply. I touch these plates, okay, so that if there's any residual charge, it goes away. I move the plates back. Now I have a candle. Okay, I have a candle. I would like to light up this candle and see what's going to happen. So this is a candle in the wind demonstration. I would like to show you ionic wind. जरा इस पे फोकस करें. Alright, now if you look at the flame, it's quite a nice flame, vertically upwards. Now this flame in itself has a world inside. इसके पूरे अंदर एक दुनिया है इस फ्लेम के अंदर. ठीक है, ये कुछ सादा सी चीज नहीं है. शायर तो कहते हैं ना कि ये शम्मा है और इस पे कई शेर लिख लेते हैं. ठीक है, गालिब ने क्या कहा था? गालिब ने कहा था जुए खू आंखों से बहने दो कि है शामे फिराक, मैं ये समझूंगा कि शमे दो फिरोजा हो गई. लेकिन शम्मा, शायर की शम्मा और है, साइंटिस्ट की शम्मा और है. इसके अंदर आयन्स हैं, इसके अंदर इलेक्ट्रॉन्स हैं, इसके अंदर कार्बन मोनोऑक्साइड है, कार्बन सूट है, नाइट्रस ऑक्साइड है, नाइट्रोजन डाइऑक्साइड है, आयन्स हैं, इलेक्ट्रॉन्स हैं. अब इसके अंदर, इन अदर वर्ड, देयर इज अ प्लाज्मा. Plasma is the fourth state of matter, which comprises ionized particles and electrons. Now these are not neutral particles. What happens when this flame is placed inside a strong electric field? Let's observe what happens. Okay, so I place this candle back in this region. Huh? Sorry? नहीं पहले तो इससे भी दिखाना नहीं. All right, let's instead of this plates, let's use needles. Okay, let's try with this first. इससे पहले. All right, so I placed this flame between the plates of my. I would need something. कोई glass plate तो नहीं लाई? Okay. इस तरह भी नहीं चलेगा. चलो, let's try. All right. Now, if I move the plates closer together, look at the pattern that this flame will take up. It's probably going to get shorter, and it's going to have two wings like a butterfly. Let's see. Or it's going to move in one direction. So what we are observing here is that the positive and negative ions and electrons, they are moving towards their respective plates of this capacitor, because the positive ions will be moving towards the negative plate, the negative ions and electrons will move towards the positive plate, and the shape of this flame is totally distorted. And you can see as if this candle flame is fluttering in a wind. That wind is ionic wind. It's being produced by ions that are moving horizontally in their respective directions with a very high speed, because they are experiencing a force and they are accelerating, they're picking up speed. Okay, I can even take a tube light. If I have a tube light like this, you can see that it will glow. I'm not connecting this with a power supply. I just place it inside the electric field, it will start glowing. This is called field emission. Because what's going to happen is that the electric field is going to ionize the gas inside this fluorescent tube light. Let me turn off the lights for a little while. अजीम जरा इसको मूव करोगे थोड़ा सा इस वाली चीज को आके, हाँ इस वाली चीज को आके ना थोड़ा सा करीब लाना. करीब लाएं. Alright, you can see the tube light glow. It's fluorescing. Right? थोड़ा सा और करो. Right? It's fluorescing. और करीब लो. So this tube light is not connected to any power supply per se. It's just placed inside an intense electric field. That electric field is strong enough that it can ionize the gas inside this fluorescent tube. And it is by virtue of this ionization and subsequent fluorescence that this tube light glows. Alright? So you can light a fluorescent tube light without connecting it to a power supply by putting it inside an intense electric field. like to write delta V equals minus in going from R to infinity. Okay? 1 over 4 pi epsilon naught. The electric field is Q over small r square. It's pointing in the radial direction dr, and I'm making a displacement dr also in the radial direction. So I'm moving along the radius from r to infinity. I don't have to move along the radius, by the way. I can move in any direction whatsoever. And the dot product ensures that I'm just taking the radial direction, because if I have ds here, the dot product of r with ds is ds cosine theta, which is a dr. So I don't have to move along the radial direction. But for simplicity, I'm assuming here that I'm moving along the radial direction. This is a point that you need to understand. I've already elaborated this in the previous lecture. So if I look at this integral, this delta V corresponds to the potential at infinity minus the potential at r. Okay, final minus initial equals minus Q over 4 pi epsilon naught. This unit products, the dot product is unity. I have dr over r square going from r to infinity. Now this is minus 1 over r. The minus cancels out of this minus. I'm left with Q over 4 pi epsilon naught 1 over r. Lower limit is r, upper limit is infinity. So I get minus Q over 4 pi epsilon naught r. And if I compare the right hand side with the left hand side, VR turns out to be Q over 4 pi epsilon naught r. I give you half a minute to look at this derivation and see if it makes sense. Silently look at it. Alright, so this electric field, according to Gauss's law, is the same as the electric field from a point charge placed at the origin. This is what we learned from the Gauss's law, because the charge is spherically distributed about the sphere. Okay, so all of this electric field is coming from the assumption that the point charge is at the origin. Likewise, this potential is coming. It's the same potential as if all the charge Q on the sphere was placed at the origin. Okay? So if I were to plot this potential as a function of small r, I will also get a curve that slopes downwards. Right? This is Q over 4 pi epsilon naught r. But which of these curves will be steeper? The top curve will be steeper. This will be a less steep curve because it's 1 over r. This one is 1 over r squared. This is hyperbolic. That one is parabolic. Okay? So now we have found out the potential outside the sphere. It drops. Okay? Now what we would like to ask is what's the potential inside the sphere? Inside the sphere, we know that the electric field is 0. Could you make a guess of what the potential inside this field is going to be? Constant? Does this mean a constant? It's going to be a straight line. At what value? Right. So this value here is Q over 4 pi epsilon naught capital R. The value here. And the potential has to be continuous, because if the potential is not continuous, it's discontinuous, the electric field will go to infinity. Okay? If this is a discontinuous function of x, then the derivative will go to infinity. That's not allowed. Electric fields can be discontinuous but not the potential. So all of this metal sphere will be at the same potential, because you have to maintain a zero electric field inside the metal. And if the electric field inside the metal is to be zero, the potential should not change with position. Okay, because the derivative is zero and the derivative of a constant is zero. So you would like to keep the potential at a stable value, and that stable value is given by this value. This is the potential inside the metal, and all of the metal is at the same potential. It's an equipotential volume, in other words. Okay, so this is a plot of the electric potential for this charged sphere versus time. Now the question is the potential inside a metal always constant? Can you think of a situation when the potential inside a metal is not constant with space? Let me write down this question. Is the potential inside a metal always constant? Alright, could anyone answer this question for me? आप में से कोई बता सकता है? आप बता सकते हो कि क्या मेटल के अंदर हमेशा पोटेंशियल कांस्टेंट रहेगा? कोई ऐसी सिचुएशन है जब वो कांस्टेंट नहीं होगा? Good point. You're pointing in the right direction. Good. That's a good point. You're pointing in the correct direction. Very good. Anyone else? Jihad. No, but inside the metal, the electric field, doesn't that have to be zero all the time? So if I have this capacitor, there's an external electric field, I place this metal inside it, the electric field inside this metal will still be zero. There will be a potential difference because there's an internal electric field that's cancelling out the external field, but the field inside is zero. So the interior of this metal is always going to be at the same potential, isn't it? Both of these questions are pointing in the right direction. Suppose I have two parallel plates. This is positively charged, negatively charged. And suppose there is air in between these plates, like this. Now I place a metal, it's producing an electric field, it's connected to the power supply, I produce a metal inside this capacitor. So I have a metal here. Now this is a metal. Now the electric field inside the metal has to be zero, which means there should be no imbalance of charges inside the metal according to Gauss's law. But this is a neutral object. This is an uncharged neutral object. Okay? Now if the electric field inside, before you place the metal, the electric field was pointing like this. So these white electric field lines are without the metal placed. So if the electric field line pattern doesn't change, it means that the electric field lines are piercing the volume. But what you really need to have is that the electric field lines do not pierce the volume of this conductor. Because in electrostatic conditions, the electric field has to be zero inside the metal. So what you need to do by virtue of Gauss's law is that these electric field lines must terminate at some point. Okay? there should be no imbalance charge inside the metal. So there's nothing stopping from the charge to accumulate on the surface. You can also view this by the fact that inside this metal, if I were to keep this electric field alive inside the metal, I would like to produce an internal electric field that balances out the electric field due to these plates in a perfectly point-to-point fashion. That is, the electric field here due to the external plates is the same as the internal electric field generated inside this metal, so that I add up the red vectors with the white vectors point to point, and the electric field inside totally goes to zero. So there are different ways of looking at it, and this production of electric field inside the metal actually means that some kind of charges are accumulating on this surface. Positive charges are accumulating here and negative charges are accumulating here. So even though this metal was initially neutral, a charge separation has taken place. Like a refrigerator. Refrigerator keeps the interior of the refrigerator cool and the outside warm. So everything is initially at the same temperature, but it creates a temperature difference. Likewise, when we place this electric field inside an external, this metal inside an external electric field, charges redistribute. So something that was initially neutral now has a positive end and a negative end. In other words, this metal becomes polarized. So the situation that we observe, initially the metal is neutral, these charges are mobile, electrons are moving, so the electrons will move toward this end of the metal and there will be deficiency of electrons here, hence this end is going to become positively charged with respect to this end. Remember, there is no movement of positive ions, it's only electrons that are moving. So this end will become negatively charged and equilibrium will then be maintained. But before equilibrium is maintained, the electric field temporarily inside this metal is non-zero. Okay? Once electric field has been maintained and the internal electric field totally cancels out the external field, will the electric field inside be zero and equilibrium will be maintained. But before the onset of equilibrium, the electric field inside this metal will not be zero. And this charge redistribution takes place on the order of picoseconds. Picosecond एक नैनोसेकंड का भी हजारवां हिस्सा है, ठीक है? माइक्रोसेकंड का मिलियन हिस्सा है. मिलियन पिकोसेकंड्स होंगे तो एक माइक्रोसेकंड बनेगा. So the equilibration takes place on the order of picosecond. So at the end, what we will have is a situation like this. The pear-shaped metal, this end will become negatively charged and all the charge will reside on the surface, no charge inside because it's an electrostatic equilibrium. Positive charge here on the surface and electric field lines will no longer be parallel, they will always be normal to the surface of the metal. So they will go like this. So the electric field lines, the electric field will not be uniform in this annular region and the field lines will not be parallel. The field vectors are changing their direction, but at the surface of the metal they are always zero. Okay, they are always zero. Oh sorry, they are always normal. Why are they normal to the surface? Can anyone tell me why these electric field lines are always normal to the surface? So if I have a metal surface like this, and it's placed inside an electric field. Suppose it's positively charged surface. The field here goes like this, here it goes like this, but here it goes like this. So the field is always normal to the surface at at the various points. Could anyone tell me why this is the case? आप इसे कोई हिम्मत करें, बता सकता है? जी आप बताएं. चार्ज अक्यूमुलेशन हो सकती है. चार्ज अक्यूमुलेशन तो इस तरह होगी जिस तरह मैं आपको दिखा रहा हूं. चार्ज अक्यूमुलेशन तो होनी चाहिए. आप पीछे बता सकते हैं, बिल्कुल पीछे. कुछ आइडिया. चार्ज होना चाहिए. चार्ज अक्यूमुलेट. जी आप बताएं. चार्ज मूव. Right, excellent. So suppose I have a surface, metal surface, straight surface, and suppose the electric field is not normal to the surface. It's at an angle. And this is my electric field. And I'm assuming everything to be in equilibrium. So if this electric field is not normal, I can resolve this electric field into two components. I can have a component parallel to the surface, and I can have a component normal to the surface. This is the parallel component. This is the normal component. Now, this normal component doesn't harm us because the electrons cannot jump outside of the metal. This normal component will have a force acting on the electrons, but the electrons cannot jump outside the metal because there is a barrier. There is an energy barrier called the work function. So this electric field that is normal to the surface doesn't harm the electrons. It does not produce any force on the electrons, which are bound by the work function. However, this component can accelerate the electrons along the surface. So the electrons or the charges will start accelerating on the surface. There will be a circulation of charge only on the surface, but that will break the condition of equilibrium because you don't allow the charges to accelerate. Therefore, this electric field is not allowed. The electric field can always be normal. And this electric field, we already know from Gauss's law, equals sigma over epsilon naught, just close to the surface of the conductor. So if the charge accumulates in some regions, there would be some regions where the charge accumulates. If the charge density is higher in those regions, the electric field is going to be higher. And I will show you now how the charge can accumulate in a certain region. But let me come to the other point of electric current flowing through a conductor. Suppose I have a copper wire, okay, and there is an electric current flowing through the wire, okay. Now the electric current can do work. The electric current can run a wheel, the electric current can light your bulb, the electric current can do all kinds of useful work, okay? Which means that the electric current can also heat a resistor, it can heat something, so it can do useful work. Now the point is that if the electric current is doing work is really force times displacement. So a force is acting on the electrons. So if electrons or positive charges, or which are the conventional charge carriers, are moving from this end to this end, and they're experiencing a force because these moving charges can do some useful work. So when they're experiencing a force, this means there is an electric field inside the conductor. All of this is metal, but still there is an electric field inside the conductor. Because without this electric field, a force cannot act on these charges. So in the case of this metal conductor, there is always an electric field that is changing its direction, but it is always along the length of the conductor. So if I look at my definitions of the potential difference, delta V, this is end A, this is end B. As positive charges go from A to B is given by VB minus VA, okay, given by VB minus VA is minus of the work done by the electric field itself, E dot dl or E dot ds from A to B. Now the electric field is always parallel to the displacement. So this dot product is between two vectors that are at an angle of 0 degrees. The electric field is always parallel to the displacement, so I can replace this integral by the electric field inside this conductor E, which is constant from point to point, although it's changing direction, multiplied by the length of this conductor, L. So this shows us that VB minus VA is a negative quantity E times L, which also tells us that A is at a higher potential than B. And this is what is happening inside a conductor that is carrying current. This is at a higher potential, which means VA is higher than VB. This is at a lower potential. So a current that is flowing through a metal always accompanies an electric field that is non-zero inside the metal. In other words, this is a non-equilibrium condition. Electric field inside a metal is a non-equilibrium condition, and it can result in a field inside the conductor, and that's what is called a current. Now, my question is that if this electric field is always there and it's accelerating the positive charges, what will be their final velocity? If you let this current flow for the entire age of the universe, or the current flows for 1 day or for 1 minute, or what's going to happen to the velocity with time? Constant ho jayegi. If there is a constant force, this is connected to a potential, this is at a high potential, low potential, constant electric field, charges are continuously flowing, what's going to happen to the velocity of these charges with time? It will keep on increasing linearly, but that means you will ultimately approach the speed of light. That's not going to happen. Why isn't it going to happen? Because every metal, no matter how good a conductor you have, say copper or gold is one of the best conductors, there's a resistance. Some of this energy is lost in overcoming the resistance. It's just like a paratrooper who's falling down. If there was just the force of gravity acting on the paratrooper, his or her velocity will keep on increasing. But then the drag force keeps on building up, and it ultimately, the paratrooper comes to a state of equilibrium. Its velocity remains constant. So in this case, the drag force, the equivalent of the drag force is the resistance. So no matter how good a conductor you have, you will always have some resistance, and the velocity cannot keep on increasing unbounded unless you're talking about a superconductor. Superconductor has zero resistance, but there is another mechanism that describes conduction in superconductors. Since you arrived late, I would like to spend another 2 minutes, promise just not more than 3 minutes, in describing one small phenomenon. Suppose I have two conductors, two metallic spheres. One has a radius A, the other has a radius B, and both of them are charged. This carries a charge Q1, this sphere carries a charge Q2, and this is a smaller sphere. And I take a wire of metal and connect the two. Now if I make this connection, this metal will be at the same potential as this metal. Okay? Because all of this is one metal now. In other words, all of this arrangement is an equipotential surface, is an equipotential volume. Everything is at the same potential. Okay? Now if I look at this surface, the potential on this surface is Q1 over 4 pi epsilon naught R A. Correct? This is the potential on this surface. ये हमने derive किया यहाँ पे. The potential on this surface is Q2 over 4 pi epsilon naught B. and both of them are equal. So I can cancel out these factors. I have Q1 over A or Q1 over Q2 equals A over B. But what is the ratio E1 over E2? What's the ratio of the electric field on the surface of sphere 1 to the electric field on the surface of sphere 2? What's this ratio equal to? कोई बता सकता है ये रेशो क्या है? A स्क्वायर ओवर B स्क्वायर क्या है ये रेशो? B स्क्वायर ओवर A स्क्वायर. This is B square over A square, because the electric field varies as the inverse of the square of the distance. Okay? Alright. Now what does this tell us? Of course there is also going to be you have to take into account the charges. So it's B square over A square into Q1 divided by Q2, right? Because you have to take into account the charge as well. So it's Q1 over A square due to the electric due to 1 and Q2 over B square due to number 2. But what is Q1 over Q2 is A over B. So I'm left with B over A. So smaller, this is E1 over E2. If B is small, E2 has to be large. If A is small, E1 has to be large. So if I shrink this volume, the electric field on the surface of this sphere is going to increase. So smaller sized objects which have a bigger curvature, smaller radius, have bigger electric fields around them. They have sharper edges, sharper points, they have more curvature. Smaller objects, they have bigger electric fields. That's why you make point conductors. In this example, this syringe needle is a pointed object. Even though this pointed object can be at the same potential as this disc, a stronger electric field will be in the vicinity of this object because it has a smaller size. Alright? So thank you very much. I'll meet half of the class in another 15 minutes with the session on uncertainties. And be careful, don't touch these syringe needles.